Hey everybody, Mr. Covey here, and I just wanted to go over 4.1 number 68 because there's kind of just one really tricky thing about it. So it says a particle, initially at rest, moves along the x-axis such that its acceleration is given by this function. So it gives us that acceleration function. And then they tell us at time 0, they give us a position of 3. Okay, so we have acceleration, and they're asking us in A about velocity and position. Okay, so the derivative of position is velocity, and derivative of velocity is acceleration, but they give us the acceleration. So how do we go backwards? Oh, we got this new thing called an indefinite integral, called the antiderivative. So how do you go backwards from acceleration to velocity? You take the antiderivative of cosine. What has a derivative of cosine? Sine. But you got this annoying Covey constant. Yeah, you can't have a function with a random Covey constant on the end. You actually have to figure out what that Covey constant is. Well, how do you find the position? Well, you do the antiderivative of that. What is the derivative of sine? Negative cosine. Sorry. What is the derivative of c? Cx, but then I'd have another Covey constant. I'll call it something. This is getting complicated. That's because you shouldn't take a second antiderivative until you solve for the Covey constant in the first antiderivative. You're like, they give me that the position equals 0, the position is 3. They don't tell me any point for the velocity. They actually do, it's just kind of hidden. They tell you the particle is initially at rest. What that means is, v of 0 equals 0. It's kind of hidden in there. Initially at rest, meaning the initial velocity is 0. So if v of 0 is supposed to equal 0, then when you plug in 0 for t, you're supposed to get out 0, meaning c is actually 0. So your velocity function is actually just sine of t. So then when you go to find your acceleration, your position function, do the antiderivative of velocity, and you get this. And again, you have to solve for this Covey constant. It's a different Covey constant than for the velocity function, because now we're having a position function. You can use a different variable if you want. You can use a Lemke constant, some people do. And how do you find that Lemke constant? Well, they tell you at t equals 0, the position is 3. So I'm going to plug in the fact that at time 0, I'm supposed to get out 3 and solve for the Lemke constant and figure out that the Lemke constant is 4, so that my position function is actually, negative cosine of t plus 4. So that's my position function. That's my velocity function. Every time you take an antiderivative, solve for the Covey constant before you take another antiderivative, if you have to take more than one. Okay, so then for B, it says find the values t for which the particle is at rest. At rest meaning the velocity equals 0. Well, when is the velocity going to equal 0? Well, when does sine of t equal 0? At t equals 0. Oh, but they just say this is for t greater than 0. So I should say like t equals pi n, where n is a positive integer, but not 0. So maybe I should say pi plus pi n, where n is a positive integer. Yeah, that'd be good. Yeah. Point is, there's infinitely many times that the velocity equals 0, multiples of pi. All right, that concludes this. Thanks for watching, guys.